In this lecture, we're going to talk about a specific kind of quantum system called the optical qubits. My name is Lin, and I'm in the group of Valerio, the same as Clive. And if you're referring to your notes, this is in the Tuesday chapter, section 2.2. So, of course, I'm going to speak specifically of the phenomenon of polarization and interference in the context of quantum mechanics. So just to make sure that we are all on the same page, in the past day, we should have learned the mathematics of quantum mechanics. This is the language of complex numbers and linear algebra. We should know how to describe states of a quantum system and describe the transformation between the states in terms of operators. And most importantly, we should know that quantum mechanics is inherently probabilistic, and we should know how to calculate the probabilities of different measurement outcomes, which is just our Bond rule. So, of course, and in the lecture that just passed, we have learned what qubits are. But I know some of you were asking, like, what actually are qubits, right? Like, where can we actually find them in real life? I think this was lampshaded a bit with some examples previously and in yesterday's talks. But so what we're going to go through is a very specific type of qubit. And so the outline of the lecture today is that I'm going to start by introducing the photon. And we're going to see how we can describe the path of a photon. How can we describe the photon is here and the photon is there, for example? And then we're going to study a specific instrument called the Mach-Zehnder interferometer and describe also the polarization of a photon. And yeah, I think that's about the outline for today. So as the name implies, optical qubits are about light, right? And one good source of light is a laser. And a laser puts out light. And so the thing is, although we like to illustrate lasers being, a beam of light, like in Star Wars and stuff, we can't actually, unless it's strong enough, it's very hard to see. And so what you do when you actually play with a laser is you would take a screen, like a piece of paper, and you would be able to see the dot on the piece of paper. But when it gets very dim, our eyes fail us. So we'll use something like a detector. And so when it's very dim, we can know whether or not the light is there. So the point of this is that if we have a detector, a specific kind of detector, which kind of, it beeps out the sound, or you connect to a computer, and it becomes quieter as the light becomes dimmer. What you'll notice is that when it gets very dim, the beeps don't get any quieter, but instead it kind of does this, it becomes discrete and random. So if you see the graph on the right, this is kind of like if you plug the detector into a computer or you are listening to the sound of the detector, you'll notice that when it gets very, very dim, instead of becoming, going to zero, right? The signal or the sound is at the same level, except that it becomes discrete and becomes random. And so this is familiar from the introduction lecture. This is the photoelectric effect. And basically what it's telling us is that light is quantum, right? It's not a continuous kind of thing. Like, it's made out of little individual packets. They are called photons. And so because of this, like, we can't use classical mechanics, and we can't say, oh, light is a wave, we have to describe it as a wave, or light is a particle, we have to describe it as a particle. It is something else entirely, and we have to use the mathematics of quantum mechanics and the framework that we have learned in the past day. So let's start with an optical experiment, right? And to do an optical experiment, we'll need some tools. For example, a window, right? A window, it transmits most of the light, but it reflects a little bit. And so, like the cat in the picture, most of the light goes through the window, but you can still see a bit of the reflection. But conversely, if you had a very thin layer of coating on the glass, then it completely reflects, right? And so if you have a layer of coating, then all the light that you shine on the mirror will reflect. And if you take the window concept, right, and you put a bit of coating, but you put just enough coating so that it reflects half of the light that it goes through and transmits the other half, then this is something called a beam splitter. And this is the key for the experiment that we'll carry out. So let's look at a beam splitter. If you shine light in, so this is a pretty bright light, right? So we know that half of the light will be detected on either of the detectors, because half of the light will go through and the other half will be reflected. And so whatever intensity you put in, half of it will be detected on the right detector and half of it on the upper detector. But what happens when you dim the light to the point where you only get single photons? Well, if you keep dimming the light, eventually you'll get back the discrete behavior of individual photons. And what you'll find is that you're still going to find a single photon at either detector 50% of the time, right? It's not going to like split into half or anything. You still get a single photon. It's just that it randomly appears either on the right detector or the upper detector. And the most important thing is that they never beat at the same time, right? You never detect the photon at both detectors at the same time. And this designation, which detector beeps the next, is completely random. You can't predict. After a single detection event, you can't predict where the next one will be. And so this tells us how we can describe where the photon is, right? Usually when you want to describe the location of something, you'd say, oh, it's in this X coordinate or Y coordinate, but it's a bit complicated. So we'll just live with two coordinates, right? So notice that you never detect the photon at two places at once, right? It's either on the right side or the upper side. It's either moving to the right or moving up. And basically, we can kind of call the one that's moving to the right moving photon, and the one that's moving up, the upward moving photon. And this is how we can describe the location of the photon, right? We have two distinct states, the right moving photon and the upward moving photon. And when you find it in one state, you will never find it in the other state. And so that is why this forms an orthonormal basis, because the inner product of these two states are zero. And notice that if you put a photon in to a beam splitter, there's a 50% chance of finding it in the right moving path or on the upward moving path. And so this tells us that the action of the beam splitter would look something like this, right? If you apply a beam splitter on a right moving photon, it will become some superposition of a right moving photon and an upward moving photon. And it's the same thing if you apply it to an upward moving photon that goes into a beam splitter. It will be some equal superposition of an upward moving photon and a right moving photon. Do take note that the signs are different if you put in an upward moving photon versus a right moving photon. And I think there's an exercise in the notes that asks you to find out why that's the case. But basically, it has something to do with making sure that the operator is unitary. Okay, so we know how to describe where the photon is, right? We just simplify everything. We just say it's either moving to the right or moving upwards. And we know what the beam splitter does to a photon. Actually, let's just check that, right? Why is the output of the beam splitter a superposition? So we can check that if we have a right moving photon, right, it goes into a beam splitter, and we claim that when it passes through a beam splitter, it kind of does this thing where it becomes a superposition of the right moving photon and the outward moving photon. And if we detect it, if we try to think of what happens at the detectors, basically we're asking, okay, if I put in a photon, a right moving photon, and pass it through a beam splitter, what is the likelihood that I will detect it on the right moving right detector? That's basically asking the probability of the right moving photon given the beam splitter after acting on the right moving photon. And conversely, the upward moving, the detector on the upper path is basically asking the question, what is the probability of finding the photon there, right? Given that I've passed a right moving photon through a beam splitter. And we have just learned how to find this out, right? If we just look at okay, this should be wrong. This should be the one that should be highlighted is the right moving photon, the rightward detector, sorry. So what's the probability of getting a right moving photon after passing a photon through a beam splitter? Well, this is just a Bond rule, right? We just take the bra of the right moving photon state, and we take the state of the photon after it goes through the beam splitter. And what is the state of the photon after it goes through a beam splitter? Well, we just claim that it is this superposition of the right moving photon and the upward moving photon. And we just expand this. We know that this is orthonormal, so this should be 1. And again, it's orthonormal, so this should be 0. And so from orthonormality, we know that the only term that survives is 1/√2. And we square this, we get half, which is 50%. So this operator does indeed describe what happens after you pass a photon through a beam splitter. And of course, like we can't just stick with beam splitters. We need to manipulate the photon a bit more to perform our experiment. So we also need something like mirrors, but this is obvious, right? If you have a mirror and you have a right moving photon, it reflects, and it reflects to the upward moving photon. And so this is just described by, if I have a mirror acting on a right moving photon, I get the upward moving photon. And the same thing, if I have an upward moving photon, it reflects to the right moving photon. So the mirror M acting on the upward moving photon just gives you a right moving photon. Okay, and this is a bit special. So what we can do, right? If I have a path here that's a right moving photon, one for the right moving photon and one for the upward moving photon, I can kind of put something there, like a thick cloth or something, right? That blocks the light. So what that does is that if I have a right moving photon, it just passes through, nothing happens to it. And if I have an upward moving photon, it gets blocked. So what I'm trying to describe is that if I apply this thing, which I call the right moving photon selector, to a right moving photon, nothing happens to it. But if I apply it to the upward moving photon, it gets blocked and you just get 0. And you can do the same thing otherwise, right? If you can block the right moving path so that when you apply the upward moving photon selector on the right moving photon, you get 0. And if you apply it to the upward moving photon, you just get back the same thing. And so this is just so that we can kind of force the photon to follow a certain path. Of course, like the cost of this is that if you have a photon that is half-half, then half of the time it will just be lost, right? Because it will just be absorbed by the thing that you block it with. Okay, so now we have enough instruments to build our Mach-Zehnder interferometer. And let's put it together, right? So the first thing you need is a first beam splitter, which is the input port. And then I'm gonna put a selector here. So I'm gonna block the upper path. So only the right photon will go through. And I'll have a set of mirrors, one final beam splitter, and a detector at the end, right? So just to gain some intuition of it, let's try to keep track of where the photon is going, okay? So let's start with the photon coming in from the right. at the bottom, at the first beam splitter. What happens immediately afterwards, we know, is that it passes through a beam splitter, and there's a 50% chance that it goes through to the right moving path, and a 50% chance that it goes to the upper moving path. And if it goes through the upper moving path, it gets blocked. And if it continues to the right, it will be flipped by the mirror. And so it will go up, and it will meet another beam splitter. And this time it passes through a final beam splitter. And there's a 25% chance that it gets detected by right detector, because there's only a 50% chance that it will go through this route. And once it meets the beam splitter, there's another 50-50 chance, right? And the other 25% chance, it will be detected by the upper detector. So let's just, we're trying to keep track of where the photon is going, and we're saying, okay, every time it meets the beam splitter, we get a 50-50 chance. But to really know what happens, we need to work it out for real, because we have this formalism, we know what the rules of quantum mechanics are, and so we have to check that our intuition was correct, okay? So let's start with the initial right-moving photon. This is just the right-moving photon state. It passes through the beam splitter, and we know that this creates a superposition in the right-moving photon state and the upward-moving photon state. And then we pass it through the selector, right-moving photon selector, right? So basically, this just blocks the upward-moving photon. So all that's left is the right-moving photon state. And then this gets reflected by a mirror, so the right becomes up, and it passes through a final beam splitter. And this just gives you another superposition. But notice that there's a extra factor that's carried over. So if we calculate the probability now that it will be detected by the right detector, this will give you the square of -½ which is 1/4, which is 25%. So indeed, there's a 25% chance that it will be detected by the right detector, and there's a 25% chance that will be detected by the upper detector. So you might be wondering what happens to the other 50%. Well, nothing happens, right? Because if it gets absorbed by the selector, then you're not gonna find it at the end. So if you repeat this whole experiment with another selector, but this time you block the right path, right? So you have a upward moving selector now. Then you also find the same thing, right? There's a 25% chance of finding it in the right path and a 25% chance of finding it in the upper path. And so the question is, what do you think will happen if we take away the blockage and we have the proper Mach-Zehnder interferometer? I'm going to try some interaction. So maybe in the chat, you can answer which of these things you think will happen, right? Do you think A, the detectors will be 50% of the time? So 50% of the time, we will find the photon on the right side, and 50% of the time, you'll find the photon on the upper side. Do you think it will be something similar, but maybe not 50-50%? Do you think only the right detector will beat, or do you think only the upper detector will beat? Maybe I think I'll give everyone 1 minute, and you can type the answer on the chat. And in the meantime, if you have any questions so far, please do ask them. Okay, don't worry, you don't have to answer. I just wanted to poll what people thought, what intuition that everyone has. So I admit that it is a bit disingenuous to kind of think of it this way. So what do I mean by this? Well, to know the actual answer, okay, maybe I shall just gauge how many people answered what. So the vast majority seems to answer A. So this is a logical choice because previously, if we have 25% for each detector, when we remove the blockage, we expect something like 50-50. And so that's a natural choice. I think there were a few that answered B. That seems to be a next. Yeah, so most people answered A, some answered B, and there was one C. Okay, so let's find out. So to really know what the answer is, we have to work it out with the rules that we have learned, right? So let's do that. Initially, we start with a state that is right moving, a right moving photon state, and then it passes through a beam splitter. So this is simply, you get a superposition of the right moving photon and the upward moving photon. Then it gets split by the mirror. So this is simple. You just sort the up for the right and the right for the up. And it passes through the final beam splitter. So I don't know why the B is, okay, there's a B there. Okay, it passes through a final beam splitter. So this, it acts on, we know how the beam splitter acts on the up state, and we know how it acts on the right state. So if we just plug in what we know previously, and you remember that I pointed out that the signs, the plus and the minus are different, right? Because the beam splitter needs to be unitary. So if we plug that in, we remove the brackets, you notice that there is a minus to the right and a plus to the right. So this actually adds up to just an up moving state. So, and what you find at the detectors at both ends are that you always find the photon at the upper path, and you never find it on the right moving path. And so this is a bit weird, like we always find it in the upward moving path. So why is there this, why do we intuitively think that we should find it at 50-50, but it doesn't actually do that? That doesn't actually happen. Well, because we kind of think, I think Clive mentioned this previously, right? Like we have this idea of randomness as, okay, every time we make a decision, we flip a coin, right? So if that was what the photon did, right? Every time, let's say it meets the beam splitter, it flips a coin. Am I going to the up? Am I going up, or am I going to the right? And then when it meets another beam splitter, it flips a coin again. Then if you kind of think of it that way, then you'll think, okay, like there's one path that goes to the right detector, and that's a 25% chance. And there's this other path that goes to the right detector, and that's also a 25% chance. Then obviously there should be a 50% chance that we find it on the right detector. But so that's not really the case, right? As we saw. So what's actually happening is that it's interfering with itself, right? To arrive at only one of the two detectors every time. And the misconception really comes in because we keep thinking, we know, okay, once we know that the photon light is discrete, right? We say, okay, like it's like a particle. And so we always say, okay, a particle goes to a beam splitter, flips a coin, goes to the right, goes up. That's not really the case, right? But it's also not really the case that it's a wave, because if it's a wave, at the end, you'll notice that you will find it at both detectors. But instead, what you find is that you only find it in either path. So it is kind of like a particle. It's also kind of like a wave, but it's neither of those, right? Like, so this is why quantum mechanics had to be introduced, because it is neither a particle nor a wave. It is something, it's a quantum object. And so these beam splitters and mirrors are not the only operations that you can apply, because I have a limited time today. I don't really have time to get into things like the phase shifter, which is basically if you have a piece of glass at one of the paths, but you don't have a piece of glass in the other path, then because the index of refraction is different, so the photon actually picks up a phase difference between the two paths. And so if you're interested, then you can look at exercise 2.26, where we look at the Mach-Zehnder interferometer with the phase shifter. And you can also have beam splitters, which are not 50-50, but maybe like 75-25 or any arbitrary ratio. And so with this, you can generate superpositions that are maybe 90% on the right moving photon and 10% the upward moving photon. And so because you can do any ratio of up and right you want, and with the piece of glass, the phase shifter, you can introduce any phase difference that you want. You can basically use all of this equipment that you have here to prepare any state that you want that is within the space of the right moving photon and the upward moving photon. And so I think here it's a good time to pause because I'm going to go on to the polarization qubit next. And so if anyone has any questions. Okay, so I'll continue the next part. So here, what we're looking at is this we're kind of asking where the photon is, right? We're looking at the location or the path of the photon. But that's not the only thing that that's not the only property that the photon has, right? Because there's this thing called polarization also. And it's easier to kind of go back to the classical picture of the wave first, and then we'll go back to the quantum picture afterwards, right? So because light is a transverse electromagnetic wave, when you say it's traveling in one direction, it's actually oscillating in some direction that is perpendicular to the direction that it's traveling in. So for example, if the wave is traveling in that direction that I illustrated here, it could be oscillating like that, or it could be oscillating like that, or anywhere in between. And so it's helpful to kind of look at these two polarizations, and we can label the blue one as the horizontal polarization and the orange one as the vertical polarization. And so this label it's arbitrary. We can label it any way we want, but once we label it, we have to stick to it. Okay. So the first thing that would be of interest is that with polarized light, you can have these things called polarizers, which you can also find in sunglasses, right? If you have a polarizer and you have a H polarizer and you have H polarized light, it's going to pass through. But if you have a H polarizer and you have a vertically polarized light, it's going to be blocked. So that's the left image there. And conversely, if you have a V polarizer, it only lets through V vertically polarized light. And what this really tells us, okay, let's continue in the classical picture, but what if we have something that is neither H nor V, right? We have a polarizer that is somewhere in between. Then this, the intensity of the light that goes through follows Malus law, right? Because if we know that if it's completely aligned, all of the light will go through. And if it's completely perpendicular, none of the light will go through. So if it's somewhere in between, we'll expect something in between, right? Some of the light to go through. And so in this case, it follows a law called Malus law, which is saying that the intensity of the output light is proportional to the cosine squared of the angle between the polarization of the light and the polarizer. So this is kind of in the classical picture. So what happens if we have, let's say, H polarized light, right? A laser that's horizontally polarized, and we dim it all the way down until we get back to the single photon picture. So we're gonna find the same thing, right? If you have H polarized light and you're shining it through the H polarizer, and you dim it down until it's single photons, it's still gonna pass through every time, right? The probability of finding a H polarized photon given a H polarized photon is always 1. And conversely, it's also true that if you shine this H polarized photon through a vertical V polarizer, you will never find it on the other end. And so the probability of finding a V photon polarized in the vertical direction is 0 given a photon polarized in the horizontal direction. And so the complementaries are also true. If you have a V polarized photon and you pass it through a H polarizer, it's not going to pass through. And if you have a V polarized photon and you pass it through a V polarizer, it's always going to pass through. So the probability is always 1. And so this should remind you of something, right? This should say, okay, actually, this kind of is an orthonormal basis, right? You have a H polarization state, you have a V polarization state, and you know that they're orthonormal, because if you find it in H, you will never find it being in the V state. And in fact, these polarizers are kind of like the H and V selectors, right? Because if you have H polarizer on H, you will just get back the same state. If you have a V polarizer on H, you will get back 0. And if you have a H polarizer on V, you'll get 0. And you have a V polarizer on V, you'll get back the same state. So these act like the selectors, like the blockers that we were talking about previously. Okay, so what happens now if we have a polarizer that is some degree away? Well, if we pass it through a theta polarizer, right, where theta is the angle between H and the polarization of the polarizer, the outcome probabilities follow a rule similar to Malus law. So if you remember, Malus law says that it's proportional to cosine squared the angle, and this is what we find. If you pass a H polarizer, photon state through a theta polarizer, the probability of finding the photon on the other side is cosine squared theta. And for the V polarized, if you pass in a V polarized state instead, you get back sine squared theta. So we know how to describe a horizontally polarized photon. We also know how to describe a vertically polarized photon. But what about, if you have something in between, right? Your photon might not be polarized in either of the states. Well, we can always describe it as some superposition of the H and V states, right? So you can have some alpha, some beta. They don't have to be real. They can have a phase difference in between. And if I gave you this state that is arbitrary polarized, you can find out what the magnitudes of alpha and beta are by just passing it through the selectors, right? Because if you pass it through the H polarizer, all of the V, the vertical components will disappear. And so from the bond rule, the probability of finding the photon passing through is just the mod square of alpha. And so it's a similar thing with the V polarizer, right? So this means that only the V component will survive, and so you'll get back beta squared. And so if you have a lot of copies of an arbitrary state and you don't know what polarization it is in, you can kind of do this process and figure out what the magnitudes of alpha and beta are. Okay, so we have established a basis, which is the horizontal and vertical polarization basis. And now we want to kind of do something cool with it, right? We want to perform operations on it so that we can do calculations. So to do that, we use something called waveplates. And so these are made out of birefringent material. So if you look at a picture here, there's a light going through and you'll see that there are 2 beams coming up. So what this is actually doing is that the index of refraction of this material, I think this should be calcite, it depends on the polarization. So for example, if you have horizontally polarized light, it might have a lower index of refraction than vertically polarized light. So if you shine it light at the angle, then you get 2 beams coming up, and each beam is polarized accordingly. So what this does is that if you have so if you shine it at the normal so that it doesn't get deflected, you'll notice that so here the fast axis is the H axis, right? So because the H axis is the fast axis, so on the V axis, you'll see that there are a lot more oscillations that go on within the material than the H axis. And so depending on the thickness of the material and depending on what the material is, what happens when it comes out is that the light components between the H component and the V component will be out of phase. There will be some phase difference between the two of them. And we can describe this by saying, okay, if I have a wave plate and it has some configuration, we can say, okay, it doesn't affect the H polarized light. But if I apply it to the V polarized light, we have some extra phase. So this is if the so-called fast axis of the material and the slow axis of the material are aligned to our H and V, right? Because if it's not aligned, something else will happen. So we call these things waveplates. Okay. If it's not aligned, so let's say I rotate the wave plate. So what happens is that, okay, I will choose the phase difference so that I will get exactly half a cycle, right? Which is pi. So if I have this but I misalign the material so that along, let's say an axis I'll call theta, nothing happens, there's no extra phase. And along the axis that is perpendicular to theta, I will gain EI pi, or a phase of -1. So if I take this and I actually apply H polarized light to it, and I apply V polarized light to it, what happens is that I will get some kind of rotation. Rotation of the polarizations, right? So basically, if I have a wave plate, I can rotate it so that I can change the polarization of my photon. And so because we need the phase difference to be pi, half a cycle, we call this a half wave plate. And so here's the thing, we have half wave plates, which can kind of do rotations. And if they're aligned, we can have some phase difference between them. And so we can use this combination of these wave plates to prepare any state that we want, right? Any polarization that we want. And the final state we can we can measure it with H polarizers and V polarizers so that we get the alpha and beta component. Or another method we can use is that if we have birefringent material and we kind of make it like a prism, two prisms actually, we can make something called a polarizing beam setter. So these are beam setters that only let through, transmits horizontally polarized light and reflects vertically polarized light. And so if you do that, if you use this and you have two detectors on either side, and I give you any state, I can measure what the H component is and what the V component is. So we've looked at two different, I guess, properties of light, right? And so the question is, what actually is an optical qubit? Well, with the first part of the lecture, we see that, okay, like if I restrict my photon, I restrict the light paths so that I can only have two paths, right? I can label, let's say, the right moving path to be called 0, and I can label the upward moving path to be called 1, right? So I call this 0, I call this 1, and I can apply any operation I want on it by using phase shifters and beam setters. And I can apply any superposition of these right moving photon and upward moving photon states. And so, but also we see that with polarized, light also has polarization, right? And it also has, we also know that the horizontal and vertical polarizations are orthonormal. And so we can label, let's say, the horizontal polarization 0 and the vertical polarization 1. And we can use different configurations of waveplates to manipulate the state and create any superposition that we want. And so I forgot who asked the question, but there was this question about what if the qubit is only describing a degree of freedom. And I think this is clearest in this slide, right? If we keep the polarization constant, right? Or we don't care about the polarization, but we have a photon that follows two different paths, then these two paths form our qubit. But on the other hand, if we keep the photon moving along a single direction, but we manipulate the polarization of the photon, then these our qubit is made up of the two polarization states. And so what actually constitutes a qubit? It depends on what degrees of freedom are available to us, right? And we can perform these quantum transformations, like whatever Pauli matrices and whatever unitary operations. And there's a corresponding way to do it in experiment by using waveplates, by using beam splitters, and so on. And so why would you learn about the qubits when, you know, there are these things? There's something specific about beam splitters, there's something specific about polarizations. Well, because once you say, okay, I have a way of saying, of creating two states that are orthonormal, and I have a way of creating any superposition of the state, and I have this mapping, right? The horizontal is always 0, the vertical is always 1. And so everything we've learned abstractly, we can apply it to whatever architecture that we have, right? It also allows us to work out ideas, to work out algorithms, and that don't depend on what your actual instruments are. And so to give a summary, I think I'm pretty early. Yeah, so to give a summary, right? Light consists of discrete packets. They are called photons. And this is why we need to describe light in terms of quantum mechanics. And if you restrict the path that a photon can take, and you restrict it to two paths, we can always describe it as a qubit. And if you apply, if you use the Mach-Zehnder interferometer, you'll see that, okay, quantum is something different from just particles and just charts, right? Because it demonstrates something that's fundamentally different, but encompassing the idea of particles and the idea of waves, right? You have a single thing, but it is interfering with itself. And so the Mach-Zehnder interferometer is a demonstration of this. And of course, we have also seen that the two perpendicular polarizations of a photon forms the basis state of a qubit. And this is going to be pretty important, I believe, for the next lecture, because one of the most common degrees of freedom that are used for entanglement procedures are with polarization.